Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a rather unusual question, a question that feels both distant and strangely close at the same time. What if our universe is not alone? What if, beyond everything we can see, beyond the furthest galaxies and the faintest light, there are other layers of reality, gently brushing against our own? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the quiet mysteries of the universe together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. For a long time, scientists held a comforting picture of the universe. It was a simple idea, almost elegant in its calmness. No matter where you looked, left, right, up, or down, the universe should appear more or less the same. Not identical in every tiny detail, of course, but balanced, smooth, fair. Imagine stirring a spoonful of milk into a cup of coffee. At first, you see swirls and streaks, little rivers of white twisting through the dark liquid. But if you keep stirring gently, eventually everything blends together into a uniform shade. No clumps, no patterns, just a quiet, even mixture. For decades, scientists believed the universe behaved in much the same way. This idea is known, in more technical language, as the assumption that the universe is uniform and directionless on large scales. But you can think of it more simply as this. Wherever you are in the cosmos, the grand view should look familiar. No special directions, no hidden edges, no preferred side of the sky. It's a beautifully calming thought. It means the universe doesn't play favourites. It means there is no secret centre, no cosmic corner where something unusual is happening. Just an endless, gentle expansion of space, unfolding evenly in all directions. And for a while, this picture seemed to work remarkably well. When scientists looked out into the night sky, mapping galaxies and clusters, they found patterns that supported this idea. Galaxies formed webs and filaments, yes, but on the larger scales, everything averaged out. Like looking at a forest from high above, you might see trees and clearings up close, but from far enough away it all blends into a soft green texture. Even more convincing was something called the cosmic background, light. This is a faint glow that fills the entire universe, a kind of leftover warmth from a very early time, long before stars or planets existed. You can imagine it like the gentle heat that lingers in a room long after a fire has gone out. When scientists measured this glow, they found it was almost perfectly even. The temperature difference from one part of the sky to another was incredibly small, only a few millionths of a degree. So small that, for a long time, it felt like confirmation that the universe truly was as smooth and balanced as we hoped. And there's something deeply reassuring about that. A universe that is calm, predictable, and evenly structured feels safe in a way. It suggests that the same rules apply everywhere, that the physics shaping distant galaxies is the same physics shaping the atoms in your body. It connects everything together in a quiet, invisible harmony. You're not in a strange or special place. You're simply part of the same gentle pattern that stretches across billions of light years. But sometimes the most comforting ideas are also the most fragile, because they rely on one key assumption: that nothing has disturbed the balance, that the cosmic coffee has been stirred perfectly, and that no external force has ever reached in to disrupt the mixture. For a long time, there was no reason to doubt this. The equations worked, the observations fit. The universe, as far as we could tell, was behaving exactly as expected. But then, slowly, quietly, new data began to arrive. Not loud, not dramatic, just small, subtle irregularities, tiny differences, slight imbalances, almost easy to ignore. At first they looked like noise, the kind of small imperfections you might expect in any measurement. After all, no instrument is perfect, no observation is completely free from error. But as the data improved and the measurements became more precise, those small irregularities didn't disappear. They stayed, and in some cases, they became clearer. It was as if, beneath the smooth surface we thought we understood, there were faint ripples, barely visible, but undeniably there, like running your hand over what seems to be a perfectly polished table, only to feel the slightest indentation. Not enough to break the surface, but enough to make you pause and wonder. Because if the universe is truly uniform, those ripples shouldn't exist. And if they do exist, then perhaps the universe is not as perfectly balanced as we once believed. Perhaps the mixture was never completely smooth. Or perhaps something touched it, something we have not yet fully understood. And as we begin to look a little closer and a little more carefully, those tiny irregularities start to form a quiet question in the background. A question that doesn't demand attention, but gently lingers. What if the universe is not completely closed? What if, instead of being a perfectly sealed system, it is just slightly open? Not enough for us to notice easily, but enough for something else to leave a mark. And as we continue, we'll begin to explore those marks one by one, gently, patiently, like tracing faint lines in the dark. Because sometimes the biggest discoveries don't begin with loud explosions or dramatic revelations. They begin with something much quieter, a small imbalance, a subtle difference, a whisper that something isn't quite the same everywhere. If you let your thoughts drift for a moment, you might imagine the universe as something vast and quiet, stretching endlessly in all directions like a calm ocean under a night sky. For a long time, that image wasn't just poetic, it was scientific. The early universe, according to our best understanding, began in an extremely hot and dense state. Everything that would one day become stars, planets, and even you was once compressed into a kind of glowing, energetic fog. Not solid, not structured, just a smooth, radiant sea of particles and light. And as the universe expanded and cooled, that fog slowly thinned out. Eventually it reached a moment when light could travel freely for the first time. Before that, light was constantly scattered, like trying to shine a flashlight through thick smoke. But as things cooled, the fog cleared, and the universe became transparent. The light released at that moment is still with us today. It fills all of space quietly, evenly, like a soft echo that never quite fades. Scientists call it the cosmic microwave background, but you can think of it more simply as the universe's earliest memory, a faint glow left behind from its childhood. And when we look at this glow, we're not just looking far away, we are looking back in time, back to a moment when the universe was only about a few 100,000 years old, a tiny fraction of its current age, which is roughly 13.8 billion years. Now here is where things become gently interesting. When scientists first measured this ancient light, they expected it to be perfectly smooth, just like the evenly mixed cup of coffee we imagined earlier. No variations, no patterns, just a uniform glow in every direction. But that's not quite what they found. Instead, they discovered that the temperature of this background light is not exactly the same everywhere. The differences are incredibly small, so small that they are measured in millionths of a degree. If you could feel it, you wouldn't notice anything at all. But with precise instruments, these tiny variations become visible. They appear as faint patterns across the sky, slightly warmer here, slightly cooler there. At first glance, these differences might seem insignificant, almost like noise, but they are anything but random. In fact, these tiny temperature variations are some of the most important features in the entire universe, because they are the seeds, the starting points from which everything else grew. You can imagine them like tiny ripples on the surface of a still pond. At the beginning, the ripples are almost invisible, but over time, gravity begins to amplify them. Regions that are just a little denser begin to pull in more matter, and as they gather more mass, their gravitational pull grows stronger, slowly, patiently. Over millions and billions of years, these small imbalances grow into something much larger. Galaxies, clusters, entire cosmic structures. Everything you see in the night sky can be traced back to these almost imperceptible differences. So in a way, the universe is not perfectly smooth, but it is nearly smooth, with just enough variation to allow structure to form. And that just enough is important. If the early universe had been completely uniform, perfectly even, then nothing would have formed. No stars, no planets, no life. Everything would have remained a thin, featureless fog forever expanding into emptiness. But if the variations had been too large, the universe might have collapsed in on itself too quickly, forming chaotic structures without stability. Instead, what we observe is something beautifully balanced. Tiny fluctuations, just the right size, small enough to preserve overall uniformity, but large enough to create complexity. It's a delicate balance, almost like tuning a musical instrument. Too tight, and the string snaps. Too loose, and it produces no sound. But when it's just right, something harmonious emerges. For many years, this picture felt complete. The universe began as a smooth, glowing field with tiny variations. Those variations grew into the structures we see today, and everything followed a set of rules that were consistent and predictable. There was a quiet confidence in that understanding, a sense that, even on the largest scales imaginable, the universe behaved in an orderly and elegant way. But as our instruments became more sensitive, and as we began to map these tiny temperature differences in greater detail, something subtle began to shift. At first, it wasn't obvious. The fluctuations were still small, still within expectations. But when scientists looked more carefully, comparing one region of the sky to another, they began to notice something unusual, not in the size of the fluctuations, but in their arrangement. Because if the universe is truly uniform on large scales, then these tiny variations should be distributed evenly in all directions. No side of the sky should stand out from another. But what if one side does? What if, instead of a perfectly balanced pattern, there is a slight preference, a faint asymmetry? Not something dramatic, not a glaring difference, just a gentle tilt, like a perfectly still lake, that is ever so slightly slanted, causing water to drift more in one direction than another. This is where the calm picture of the universe begins to shift, not with a loud contradiction, but with something much quieter, a pattern that seems just a little off. And the more carefully we look, the more that subtle imbalance begins to reveal itself. It doesn't break the theory outright. It doesn't shatter our understanding, but it introduces a small, persistent tension, a feeling that something in the background isn't entirely symmetrical. And as we continue, we'll begin to explore that imbalance more closely, because sometimes the most important discoveries don't come from things that are wildly different, but from things that are almost the same, just not quite. As we continue drifting through this quiet picture of the early universe, it's helpful to pause for a moment and imagine what scientists were expecting to see before the data became as precise as it is today. If the universe truly follows that gentle idea of balance, if it really is the same in every direction, then no matter where we look, the patterns in that ancient background light should feel evenly spread, not identical, but fair, like tossing a handful of sand across a flat surface. There may be small clusters here and there, but overall nothing should favour one side over another, no preferred direction, no hidden tilt. And for a long time, that expectation held. But then came a new generation of instruments, more sensitive, more precise, able to measure those tiny temperature differences in the cosmic background light with extraordinary accuracy. One of the most important of these was a space observatory designed to map the sky in incredible detail. It didn't just glance at the universe, it carefully traced it, point by point, like someone slowly running their fingers across a surface, feeling for imperfections. And what it found was subtle, not dramatic, not overwhelming, but enough to make scientists pause. When the full map of the sky was assembled, something unexpected appeared. The two halves of the sky didn't quite match. One side seemed slightly different from the other. Not by much, just enough to be noticeable when measured with precision. A faint imbalance, a gentle asymmetry. If you imagine the universe as a sphere surrounding you in all directions, this discovery suggested that the sphere wasn't perfectly even. It was ever so slightly distorted, like a ball that has been pressed on one side. You might not notice it at first glance, but once you know it's there, it becomes difficult to ignore. This effect is sometimes described in technical language as a kind of hemispherical asymmetry, but you can think of it more simply as this. One half of the sky appears just a little different from the other, and that raises a quiet but important question. Why? Because according to the idea of a uniform universe, there shouldn't be a special half of the sky. There shouldn't be a direction that stands out. Everything should average out. And yet, it doesn't. Now, it's important to be gentle with this idea. Science doesn't jump to conclusions. When something unexpected appears, the first instinct is not to assume something extraordinary, but to ask simpler questions. Could this be a measurement error? Could it be an artifact of the instrument? Could it be a statistical coincidence? A rare but possible fluctuation that just happens to look meaningful? These are all reasonable possibilities, and scientists have spent years carefully testing them, checking the instruments, reanalyzing the data, comparing results from different observations. Because sometimes what looks like a pattern is just noise, like seeing shapes in clouds or faces in the shadows of a room. The human mind is very good at finding patterns, even when they aren't really there. But the more the data was examined, the more this asymmetry remained. It didn't disappear under scrutiny. It didn't fade with better measurements. It persisted, quietly, consistently. And that persistence is what makes it interesting, because a single irregularity can often be explained away, but a pattern that stays, even as our tools improve, begins to feel more like something real. Still, it's important to keep our feet on the ground. Even now, this asymmetry is not considered definitive proof of anything extraordinary. It's subtle, it's debated, it sits in that delicate space between interesting anomaly and clear evidence. And yet it introduces a kind of tension into the story of the universe, because it gently challenges one of our most comfortable assumptions, that everything on the larger scales is evenly distributed, that the universe has no preferred direction, that it is, in a sense, perfectly fair. But what if fairness is only approximate? What if the universe is mostly balanced, but not entirely? Like a table that looks flat but causes a marble to roll ever so slightly in one direction. Not enough to be obvious, but enough to matter over time. Because even a tiny imbalance, when allowed to act over billions of years, can lead to noticeable effects. It can influence how matter gathers, how structures form, how motion unfolds, and perhaps even how we interpret the universe itself. There's something quietly profound about that idea. That perfection might not be required. That the universe doesn't have to be flawless to be understandable. It can be almost uniform, with just a hint of imperfection. And that hint may carry meaning, or it may simply be one of those rare fluctuations that happen in any large system. At this stage, we don't yet know. And that uncertainty is not a weakness. It's part of the process. Science often moves forward not by finding immediate answers, but by learning how to ask better questions. And this asymmetry is one of those questions, a soft, persistent one. Why is one side of the sky slightly different? Is it a coincidence, a statistical ripple, or a subtle sign that something, somewhere, has influenced the universe in a way we don't yet fully understand? For now, we simply observe. We note the imbalance. We let it sit in the background of our understanding. And as we move forward, we begin to place it alongside other anomalies, other small irregularities that, on their own, might seem insignificant, but together may begin to form a pattern. Because sometimes a single uneven surface is easy to dismiss, but when you start to feel the same slight tilt again and again, you begin to wonder whether the floor itself is not as level as you once believed. And that is where our journey gently continues. As we continue gently exploring these subtle imbalances in the sky, it becomes clear that the asymmetry we just described is not the only quiet irregularity scientists have found. There is another feature, one that sits quietly in a specific region of the cosmos, almost like a faint mark on an otherwise smooth surface. It is known as the cold spot. At first, the name might not sound particularly dramatic. After all, space itself is already extremely cold. The average temperature of the cosmic background light, the faint glow that fills the universe, is only about 2.7 degrees above absolute zero. That's just a little warmer than the coldest temperature physically possible. So when we say cold, we don't mean cold in the everyday sense. We mean slightly colder than expected. But even a small difference can carry meaning. The cold spot is a region in the sky where this ancient background light is noticeably cooler than the surrounding areas. Not by much, again just a tiny fraction of a degree, but enough to stand out when scientists map the sky with precision. If you were to visualize it, it would look like a faint blue patch against a mostly uniform field. Subtle, quiet, easy to overlook unless you know where to look. And for a while, that's exactly how it was treated, as just another small fluctuation, because as we've seen, tiny variations are expected. They are part of the natural texture of the early universe, little ripples that eventually grow into galaxies and clusters. So at first, the cold spot didn't seem too unusual, but as the data improved, and as scientists examined it more carefully, something began to stand out. This particular region wasn't just slightly different, it was larger than expected, and colder than expected, almost as if the ripple had been stretched, or deepened, beyond what standard models would predict. To understand why this matters, it helps to return to a simple idea. In the early universe, those tiny temperature differences correspond to slight differences in density, how much matter was present in a given region. A slightly cooler region often means that photons, the particles of light, lost a bit more energy as they travelled through space, and that can happen if they pass through a region with less matter, a kind of cosmic emptiness. So one of the first explanations for the cold spot was that it might be caused by a large region of space with fewer galaxies than usual, a vast, quiet void. Imagine travelling through a city at night. Most areas are filled with lights, buildings, street lamps, passing cars. But every now and then you might pass through a dark stretch where the lights are sparse, where everything feels just a little emptier. The cold spot could be something like that, a cosmic region where matter is less concentrated. And indeed, when astronomers looked in that direction, they found evidence of a large-scale structure known as a supervoid, a region of space that contains significantly less matter than average. This particular one is enormous, spanning hundreds of millions, even up to around 1 billion light-years across. To put that into perspective, our entire galaxy is only about 100,000 light-years wide. So this void is thousands of times larger than the Milky Way, a truly vast emptiness. Now, here's where things become gently puzzling. Even with such a large void, it's not entirely clear that it can fully explain the cold spot. The effect that a void has on passing light is understood. As light travels through an underdense region, it can lose a small amount of energy, leading to a slight cooling in the observed temperature. This process is sometimes described in more technical terms, but you can think of it simply as light climbing out of a shallow gravitational dip. Like a ball rolling up a gentle slope, it loses a bit of energy along the way. But when scientists calculate how much cooling a void of this size should produce, the numbers don't quite match what we observe. The cold spot appears just a little too cold, not dramatically so, but enough to raise questions, and this is where the story becomes more interesting. Because once again, we are faced with something that doesn't quite fit perfectly. Not a contradiction, not a failure of the theory, but a small tension, a quiet mismatch between expectation and observation, and as before, there are several possible explanations. It could still be a statistical fluctuation, an unlikely but not impossible variation in the data. In a universe this large, rare events can and do happen. Or it could be that our understanding of large-scale structures, like voids, is incomplete. Perhaps there are effects we haven't fully accounted for yet, but there is also a more speculative possibility, one that is approached carefully and with caution. What if this region is not just a natural feature of our universe? What if it is a mark? Not necessarily a dramatic scar or a violent disruption, but a subtle imprint, the kind of gentle disturbance that might occur if something interacted with our universe in the distant past, something that left behind a slight imbalance, a faint trace. Now, it's important not to rush toward that conclusion. Science moves slowly, especially when dealing, especially with ideas this profound. Extraordinary claims require extraordinary evidence, and at this stage the cold spot alone is not enough to confirm anything beyond our current understanding. But it does something important. It adds to the pattern. It joins the asymmetry we discussed earlier. Another small irregularity, another gentle deviation from perfect uniformity. And when these features begin to accumulate, even quietly, they invite us to look a little closer, to ask whether they are truly independent, or whether they might be connected in some deeper way. Because a single quiet void can be dismissed, but when multiple subtle features begin to point in similar directions, they start to feel less like isolated accidents, and more like pieces of a larger puzzle, a puzzle that we are only just beginning to see. And as we continue, we'll begin to explore whether these quiet irregularities, these faint marks in the sky, might not be random at all, but part of a broader pattern that gently reshapes how we think about the universe itself. If you sit with the idea of the cold spot for a moment, letting it settle gently in your mind, you may begin to notice something curious about it. It is not just that this region is slightly colder than expected, it is that something seems absent, as if a piece of the universe that should be there simply isn't. To understand why this matters, it helps to return to a very simple principle. In the large-scale universe, matter tends to spread out in a fairly balanced way. Not perfectly even, of course, but predictable enough that we can estimate how much matter should exist within a given volume of space. Imagine standing in a wide forest. If you mark out a large enough area, say a square kilometre, you would expect to find roughly a certain number of trees. Some patches might be denser, others more sparse, but on average the distribution becomes reliable. Now imagine walking into a region of that forest where, instead of finding slightly fewer trees, you find almost none. Not just a clearing, not just a meadow, but an enormous stretch of land where the trees simply never grew. That is the feeling scientists began to have when they looked more closely at the region associated with the cold spot. This area is linked to what is known as a supervoid, a vast region of space with significantly less matter than expected. But this is not just a small dip in density, it is immense. So large that it stretches across hundreds of millions of light years, possibly approaching a scale close to 1 billion light years across. To give that some perspective, light itself, moving at about 300,000 kilometers every second, would take nearly 1 billion years just to cross from one side of this region to the other. That's not a gap. That's an absence on a cosmic scale. Now, at first glance, voids like this are not entirely surprising. The universe forms a kind of cosmic web, where galaxies cluster along filaments, leaving behind empty spaces in between. These voids are a natural part of how matter organizes itself under gravity. But even within that framework, there are limits. Gravity takes time to move matter. It takes time for galaxies to drift, for regions to empty out, for structures to evolve. And when scientists estimate how long it would take for a void of this size to form naturally, simply through the slow pull and push of gravity, the numbers begin to feel stretched. Not impossible, but uncomfortable. Because the universe itself has a finite age, about 13.8 billion years. That is the total amount of time available for all structures to form, evolve, and settle into the patterns we see today. So the question becomes, has there been enough time for such a vast region to become so empty through natural processes alone? And the answer is not entirely clear. Some models suggest it might be possible under the right conditions. Others suggest that it would be extremely unlikely, and that word, unlikely, begins to appear more often. Not impossible, but rare. And when rare things appear once, we tend to accept them. But when they begin to appear alongside other rare features, like asymmetries in the sky or unusual temperature patterns, we start to pay closer attention. Because patterns made of rare events are no longer just random. They begin to hint at something deeper. Now, there is another layer to this puzzle. Even if we accept that such a large void exists, we still have to ask, does it fully explain what we see? As we mentioned earlier, light passing through an underdense region, through a void, can lose a small amount of energy. This can make the region appear slightly cooler in the cosmic background map. But when scientists carefully calculate the expected effect of this supervoid, the numbers don't quite match the observed cooling. The void explains part of the cold spot, but not all of it. It's as if you found a large empty space in the forest, but not large enough to explain why the entire region feels so unusually quiet. There is still something missing from the explanation, and that creates a kind of gentle tension, not contradiction, but an incomplete picture, a sense that we are seeing part of the story but not the whole. This is where science becomes both careful and curious, because when an explanation almost works, but not quite, it invites us to look more closely, to refine our models, to ask whether there are additional factors we haven't considered, or whether the assumptions we started with might need to be adjusted. And one of those assumptions, as we've already begun to explore, is the idea that the universe is fully self-contained, that everything we observe can be explained by processes happening entirely within our own cosmic system. But what if that assumption is only mostly true? What if, in rare cases, the system is influenced by something beyond its usual boundaries? Now, again, this is not a conclusion. It is simply a possibility, one that sits quietly at the edge of our understanding. But the missing matter problem, the fact that this vast region appears emptier than expected and colder than fully explained, adds another small piece to the puzzle. It suggests that something about this region is unusual, not dramatically so, but enough to stand out, enough to resist a complete explanation, and enough to make us wonder whether we are looking at a purely internal feature of the universe, or something that has been gently shaped by influences we do not yet fully understand. Because sometimes, when you walk into a quiet clearing in the forest, and everything feels just a little too still, you begin to wonder not just what is there, but what might have been there before, and what might have caused it to disappear. As we sit with these ideas, the cold spot, the vast, supervoid, the quiet sense that something doesn't fully add up, it becomes helpful to step back and ask a slightly different kind of question. Not what we are seeing, but how likely it is that we would see it at all. Because in a universe as large as ours, unusual things are bound to happen from time to time. With billions of galaxies, trillions of stars, and immense stretches of space, even rare events can occur simply by chance. Like shuffling a deck of cards long enough, eventually you will encounter hands that feel strangely ordered. And so, when scientists first encounter an anomaly, the most cautious explanation is often the simplest one. Perhaps it is just randomness, a fluctuation, an unlikely but not impossible arrangement of data. But there is a quiet threshold where randomness begins to feel less convincing. To understand this, imagine sitting in a room filled with air. The molecules around you are in constant motion, bouncing in all directions, colliding, spreading out evenly. Now, in theory, it is not impossible for all of those air molecules to suddenly drift into one corner of the room, leaving the rest of the space empty. The laws of physics do not forbid it. But the probability is so incredibly small that in practice we never expect it to happen. Not once, not ever. And if it did happen, even briefly, we would not call it a coincidence. We would suspect that something else was at work. This is the kind of thinking that begins to emerge when scientists look at features like the cold spot and its associated void. Because while each individual anomaly might be explained as a rare fluctuation, the degree of rarity matters. There is a way scientists describe this idea using something called statistical significance. In simple terms, it measures how likely it is that a result could occur purely by chance. Instead of using abstract symbols, we can think of it in terms of confidence. A low significance means something could easily be random. A high significance means it is very unlikely to be random. And when we begin to reach levels where the probability of chance becomes extremely small, so small that it feels almost impossible, we start to take notice. Now, in the case of the cold spot, estimates vary depending on how the data is analysed. Some studies suggest that the chance of such a feature appearing randomly might be on the order of a few percent. That may not sound especially small at first, but it's important to remember that this is not a single isolated measurement. It sits alongside other irregularities, like the asymmetry in the sky we discussed earlier. And when multiple unlikely features begin to appear together, the situation changes. Because probabilities don't simply add, they compound. It's like flipping a coin. Getting heads once is not surprising. Getting heads 5 times in a row begins to raise an eyebrow. Getting heads 20 times in a row would make you wonder whether the coin is truly fair, not because it's impossible, but because it becomes increasingly unlikely. In much the same way, the universe is presenting us with a handful of features that, individually, might be acceptable as rare fluctuations, but together begin to feel less like coincidence and more like a pattern. Still, science remains careful, because there is always a risk of seeing meaning where there is none. Humans are natural pattern seekers. We are wired to connect dots, to find structure, to impose order on randomness. Sometimes we see constellations in the stars, shapes and stories that are not really there. So scientists must guard against that instinct. They ask difficult questions. Are we selecting these anomalies after the fact simply because they stand out? Are we underestimating how often such patterns might occur in a universe this large? Are there biases in the way we collect or interpret the data? These are not easy questions, and they do not have simple answers, but they are essential. Because the line between rare but natural and evidence of something new is a delicate one, and crossing it too quickly can lead us astray. So instead of jumping to conclusions, scientists take a slower path. They gather more data, they compare observations from different instruments, they test different models, and most importantly, they wait to see whether the anomalies persist. Because persistence is key. A random fluctuation may appear once, but it's less likely to appear again in the same way. But a real effect, something rooted in the structure of the universe, will tend to remain, even as our measurements improve. And that is what makes the current situation so quietly intriguing. Because these anomalies have not simply disappeared with better data. They remain, not perfectly consistent, not universally agreed upon, but present enough to keep the question open. And so we find ourselves in an interesting position. We are not looking at clear evidence, but we are no longer looking at simple noise either. We are somewhere in between, in a space where the data is just uncertain enough to resist firm conclusions, but just unusual enough to invite deeper curiosity. And that space, this space between certainty and mystery, is often when new ideas begin to take shape. Because when randomness stops being entirely convincing, we begin to consider other possibilities, gently, carefully, without rushing. And one of those possibilities is this: what if these patterns are not entirely internal? What if they are not just the result of processes unfolding within our universe, but are in some subtle way influenced by something beyond it? Not something dramatic, not something obvious, but something quiet, something that does not break the structure of the universe, but slightly shifts it. Like a faint current beneath the surface of still water. You might not see it directly, but over time it leaves a trace. And as we continue, we'll begin to explore whether these traces, these quiet deviations from perfect randomness, might point towards something larger, something just beyond the edge of what we can observe. If you allow your thoughts to linger for just a moment on where we left off, there is a quiet feeling that begins to take shape. Up to now, each irregularity we've explored, the slight imbalance across the sky, the cold spot, the vast region where matter seems to be missing, could still be understood on its own. Each one, taken separately, might be explained as a rare fluctuation. Unlikely, yes, but not impossible. And yet, there is something subtle that begins to shift when we stop looking at them in isolation and instead begin to look for connections. Because if these features are not entirely random, then they may not appear alone. They may leave traces, not loud or obvious ones, but faint, repeating impressions, almost like echoes. And this is where another curious idea begins to emerge from the data. When scientists study the ancient background light, the faint glow left over from the early universe, they don't just look at temperature differences, they also examine how those differences are arranged, the shape of the fluctuations, the patterns they form across the sky. And in some analyses, researchers have noticed something intriguing. Not a single spot, not a single irregular patch, but hints of circular patterns, faint rings, subtle structures that seem to form gentle, round outlines across the cosmic background. Now, it's important to approach this carefully. These circles are not sharply defined. They are not perfect geometric shapes drawn across the sky. They are soft statistical features, patterns that emerge only when the data is processed and examined in certain ways. If you were to look at the sky with your own eyes, you wouldn't see them. But when scientists map the temperature variations and analyze the data, these circular features begin to appear, quietly, almost like impressions left behind. A helpful way to imagine this is to think about a still pond. If you drop a small pebble into the water, it creates ripples that spread outward in circles. Now imagine that the pond is very large, and the ripples are extremely faint. So faint that, at first, you might not notice them at all. But if you observe carefully, perhaps from above, you might begin to see the gentle outlines of those waves. Not strong, not obvious, but present. And if more than one pebble were dropped, you might begin to see overlapping rings, multiple ripples, intersecting and fading into one another. This is somewhat similar to how these circular patterns are described, not as sharp boundaries, but as faint echoes of something that may have disturbed the early universe. Now, one possible explanation for these patterns is entirely internal. They could arise from natural processes in the early universe, random fluctuations that by chance happen to align in ways that create circular features. Given enough data and enough complexity, the human mind can detect shapes even in randomness. So again, caution is essential, but there is another possibility, a more speculative one. And like everything we've discussed so far, it is approached gently without certainty. Some theoretical models suggest that if our universe had interacted with another region, another bubble of space during its earliest moments, it could leave behind a specific kind of imprint. Not a chaotic disruption, but a smooth, circular disturbance, like two soap bubbles gently touching. When bubbles meet, they don't shatter each other. They press softly, creating a boundary, a curved surface where the two meet. If something like that had occurred in the very early universe, it might leave behind a subtle mark, a circular region where the properties of space are just slightly different, and over time, as the universe expanded and cooled, that mark could stretch and fade, becoming part of the background pattern we observe today. Not obvious, but detectable with careful analysis. Again, this is not a confirmed explanation. It is a possibility, one that sits alongside more conventional interpretations. But what makes it interesting is not just the idea itself, it's how it connects with the other anomalies we've already seen. Because now, instead of a single unusual feature, we begin to see the suggestion of repetition. Not one mark, but several faint echoes. And when patterns begin to repeat, even softly, they become harder to dismiss. Imagine walking across a smooth floor and noticing a single small dent. You might ignore it. But if you continue walking and feel another dent, and then another, all spaced in a similar way, at some point you begin to wonder whether the surface itself is not as uniform as it appears, whether something has shaped it, not dramatically, but consistently. And that is the quiet shift that begins to happen here. We move from asking, is this one feature unusual, to asking, are these features connected? And that question changes everything. Because if they are connected, then they may share a common cause, and that cause may not be something local or random. It may be something more fundamental, something that affected the universe on a larger scale. Perhaps even something that lies beyond what we can directly observe. Still, we remain careful. These circular patterns are debated. Different analyses produce different results. Some studies find evidence for them, while others do not see the same structures with the same clarity. This is the nature of science at the edge of knowledge. The signals are faint, the interpretations are uncertain, and the truth often reveals itself slowly over time. But even in this uncertainty, there is something quietly compelling, because the idea of faint repeating patterns, soft echoes in the fabric of the universe, adds another layer to the story we are beginning to uncover. It suggests that the irregularities we see may not be isolated accidents. They may be related. They may form a pattern, and patterns, even subtle ones, invite us to look deeper, to listen more carefully, to ask not just what we are seeing, but what might have left these traces behind. And as we continue, we'll begin to gather these pieces together, these quiet anomalies, these faint echoes, and see whether they form something more than coincidence, something that begins to feel intentional, not in the sense of design, but in the sense of connection. If you let your thoughts settle gently on those faint circles, those soft, almost invisible ripples in the background of the universe, a quiet shift begins to take place. At first, each anomaly felt separate, a small imbalance in one direction, a slightly colder region in another, a vast emptiness where matter seemed to be missing, and now perhaps faint circular patterns, like echoes of something that once passed through. Individually, each of these can still be explained away. They can be treated as rare events, statistical fluctuations, the natural imperfections of a universe that is large enough to contain a little bit of everything. But something changes when we stop viewing them as isolated, or when we place them side by side. Because patterns do not always announce themselves loudly. Sometimes they emerge slowly, almost reluctantly, as the mind begins to connect what once seemed unrelated. It's a bit like noticing small dents on a surface. If you find one dent on a table, you might assume it was an accident. If you find two, you might still dismiss it. But if you run your hand across the surface and feel several dents, subtle but spaced in a way that feels intentional, you begin to sense that something has shaped the table, not randomly, but with some underlying cause. And that is the quiet transition we're entering now, from accident to pattern. Not confirmed pattern, not a clearly defined one, but a possibility that begins to take form. Because when scientists examine the cosmic background, the faint glow that carries the memory of the early universe, they are not just looking for single anomalies, they are looking for consistency, for repetition, for structures that appear in more than one place or in more than one way. And what they have found over time is that several of these irregularities seem to point in similar directions. Not literally, but conceptually. They all suggest that the universe may not be perfectly uniform, that there may be slight preferences, subtle imbalances, faint distortions. Now it is important to remain grounded here. This does not mean the universe is chaotic or broken. Far from it. On the larger scales, it is still remarkably smooth and well behaved. The overall picture remains intact, but within that picture there are small deviations, and those deviations seem to cluster. They appear in ways that feel just a little too consistent to ignore entirely. For example, we have the asymmetry in the sky, one half slightly different from the other. We have the cold spot, larger and colder than expected. We have the supervoid, an immense region where matter appears to be missing, and now possibly faint circular patterns, suggesting echoes of past disturbances. Each of these is subtle. Each of them sits just at the edge of what we can confidently interpret. But together they begin to form something more. Not a clear picture, but a direction, a suggestion. Like faint footprints that only become visible when you step back and see the whole path. And this is where the emotional tone of the story begins to shift, very gently, not towards certainty, but toward curiosity. Because once a pattern is suspected, the question naturally changes. We're no longer asking, is this one feature unusual? We begin asking, could these features share a common origin? And that question opens the door to something deeper. Because if multiple anomalies are connected, then they may not be independent events. They may be different expressions of the same underlying cause, something that has influenced the universe on a scale larger than any one region. Now, again, we move carefully. There's always the possibility that what we are seeing is still the result of chance. Even multiple anomalies can arise randomly in a system as vast as the universe, but as more data accumulates, and as these features continue to appear, even in slightly different forms, the idea of pure coincidence begins to feel less comfortable, not impossible, just less satisfying. And when explanations begin to feel incomplete, science does what it always does. It begins to explore alternatives, gently, cautiously, without abandoning what we already understand, but allowing space for new ideas to emerge. And one of those ideas, still soft, still uncertain, is that these patterns may not originate entirely from within our universe, that they may be influenced by something beyond it, not something dramatic, not something that breaks the laws of physics, but something subtle, something that leaves behind faint traces, like a breeze moving across a still surface, creating patterns that reveal its presence, even though you cannot see the breeze itself. This is not yet a conclusion. It is simply a shift in perspective, from seeing the universe as a perfectly closed system to considering the possibility that it may be slightly open, not enough to be obvious, but enough to allow for interaction, enough for influence, enough for a pattern to emerge. And as we continue, this idea will begin to take a more defined shape, because if there is an external influence, if something has in some way touched or affected our universe, then we might expect to see not just structural patterns, but motion, a subtle, coordinated movement, a sense that large regions of the universe are not entirely still, but are being gently guided in a particular direction. And that is where our journey begins to drift next, from patterns to motion, from marks to movement, from quiet traces to something that flows. As these quiet patterns begin to gather in your mind, subtle imbalances, faint circular traces, regions that seem emptier than expected, there is a gentle question that naturally begins to form. Not a loud question, not a dramatic one, but something softer. What if these are not just patterns within the universe, but impressions left on it? Up to this point, we have been looking inward. We have asked whether the universe itself, through its own internal processes, could produce these irregularities, and in many cases the answer is still yes. The universe is vast enough, complex enough, and old enough to generate a wide range of structures, even unusual ones. But now, as those anomalies begin to feel less isolated and more connected, it becomes reasonable to consider another possibility. A possibility that does not replace our current understanding, but gently extends it. What if the universe is not entirely alone? To explore this idea, it helps to imagine something very simple, a collection of soap bubbles, Each bubble is its own space with its own boundary, its own surface, its own interior. If you look at one bubble by itself, it appears complete, self-contained. But when bubbles gather together, they sometimes touch. And when they do, something interesting happens. They don't burst immediately. They don't merge into chaos. Instead, they press gently against each other. At the point of contact, a thin boundary forms, a curved surface where the two bubbles meet. That surface is different from the rest of each bubble. It carries a trace of the interaction, a subtle distortion. Now imagine that something like this happened, not with soap bubbles, but with entire regions of space. In some models of the early universe, space itself may have expanded in such a way that multiple regions formed, each one growing, evolving, and separating from the others. You can think of them as bubbles in a vast cosmic foam, each one a universe of its own. Most of these bubbles would never interact. They would drift apart, carried by the expansion of space. But occasionally, two might come close enough to touch, not violently, not catastrophically, but gently. And if that happened, the interaction might leave behind a mark, not something obvious, not a dramatic scar, but a smooth, extended feature, a circular region, a slight variation in temperature, a subtle distortion in the structure of space, something that would, over time, become part of the background pattern we observe today. Now, it's important to pause here and take a breath, because this idea, while fascinating, is still speculative. It is not confirmed, it is not widely accepted as fact. It is one of several possibilities scientists consider when trying to explain features that don't quite fit within standard expectations, and yet it has a certain quiet appeal, because it offers a way to connect several of the anomalies we've discussed. The cold spot, with its unusual size and temperature, the possible circular patterns like ripples in a pond, the subtle asymmetry across the sky. Each of these could, in principle, be consistent with a gentle interaction, something that nudged the early universe in a particular way, not enough to disrupt it, but enough to leave a trace. And that idea changes how we think about the universe, not in a dramatic, overwhelming way, but in a subtle shift of perspective. Instead of imagining the universe as a completely sealed system, perfectly isolated, untouched, we begin to consider the possibility that it may be part of something larger, a broader landscape, a wider structure, where interactions, though rare, are not impossible. Now, this does not mean that other universes are close in any everyday sense, not close like neighbouring cities, not even close like distant galaxies. If such regions exist, they may be separated in ways that are difficult to imagine, perhaps not just by distance, but by different dimensions or layers of space. But even then, under certain conditions, interactions might still occur, especially in the earliest moments, when everything was much closer together and the structure of space itself was still taking shape. In that sense, any interaction we observe today would not be happening now. It would be a relic, a memory, something that occurred long ago when the universe was still young, and like the faint glow of the cosmic background light, it would have stretched and faded over time, becoming softer, more diffuse, more difficult to interpret, but not entirely gone, still present, still detectable, if we know how to look. Of course, there are many reasons to be cautious. Other explanations remain entirely possible. The anomalies could still be statistical. They could arise from processes we do not yet fully understand within our own universe, and science, as always, resists the temptation to jump to the most extraordinary conclusion. But the idea of interaction, of gentle contact between regions of space, offers something valuable, not certainty, but coherence, a way to see these scattered irregularities as parts of a single story. A story in which the universe is not perfectly isolated, but quietly connected, Not obviously, not directly, but subtly, like two surfaces that have touched and then moved apart, leaving behind only the faintest trace of their encounter. And if that is even partially true, then the universe we see today may carry within it the memory of something beyond itself. A quiet reminder that what we observe may not be the whole picture, and as we continue, we will gently shift our focus from these possible traces of past interactions to something else entirely, not marks left behind, but motion. Because if there are influences beyond what we can see, we might expect not just patterns, but movement. A slow, coordinated drift. A sense that the universe, on its largest scales, is not entirely still. As your thoughts drift from the idea of faint marks, subtle traces that may have been left behind long ago, it can feel natural to ask a slightly different kind of question. If something has influenced the universe from beyond what we can see, would we only find evidence in patterns, or might we also find it in motion? Because while patterns tell us about the past, about what may have happened, motion tells us something about the present. It reveals how things are behaving now, and in a universe as vast as ours, motion carries meaning. But before we look at what has been observed, it helps to return once again to what we would expect, because expectation is a quiet anchor. It gives us something to compare against, a sense of what normal should look like. Imagine for a moment a large swarm of bees. Each bee moves on its own, following simple rules, responding to its neighbours, drifting through space in a kind of organised chaos. If you step back and observe the swarm from a distance, you may notice that while individual bees move in different directions, the swarm as a whole does not drift strongly in any one direction. There is motion, certainly, but it balances out. Random movements cancel one another. The swarm stays roughly where it is. This is similar to how we expect matter to behave on the larger scales of the universe. Galaxies move. Clusters of galaxies move. Everything is in motion, influenced by gravity, expanding space, and the distribution of matter. But when we zoom out far enough, looking at truly enormous regions of space, those motions should average out. There should be no strong preferred direction, no large-scale drift. Because if the universe is roughly uniform, then the gravitational pulls from all directions should balance. Like many small hands gently tugging in different directions, but none strong enough to dominate. This idea is deeply connected to the same assumption we explored earlier, that the universe is, on large scales, evenly distributed. And if that is true, then large-scale motion should be calm, unbiased, without a clear direction. Now, this doesn't mean everything is still, far from it. On smaller scales, motion can be quite dramatic. Galaxies orbit within clusters. Clusters interact with one another. There are regions where matter is more concentrated, creating stronger gravitational pulls. In those areas, motion becomes more structured, more directional. But as we expand our view, looking at larger and larger volumes of space, these local motions should begin to cancel out. The universe, in its grandest view, should feel still, or at least evenly active in all directions. There is another way to think about this. Imagine placing a small leaf on the surface of a calm lake. If the lake is truly still, the leaf will drift only slightly, nudged by tiny currents, perhaps moving a little this way or that. But there will be no strong, sustained movement in one direction. Now imagine that, instead of a calm lake, there is a hidden current beneath the surface, a slow, steady flow that gently carries the leaf across the water. At first, the movement might be subtle, almost unnoticeable, but over time, it becomes clear that the leaf is not just drifting randomly. It is being guided, pulled, moved in a particular direction. In the expected picture of the universe, there should be no such hidden current on the larger scales. no unseen force that gently pulls vast regions of space in a single direction. Everything should balance, everything should average out, and for a long time, this expectation seemed reasonable. Observations of galaxies and clusters generally supported this view. Motion was present, but it appeared to be local, influenced by nearby structures, not by something vast and unseen. But as with the patterns we explored earlier, the story begins to shift when measurements become more precise. Because when scientists began to examine the motion of galaxy clusters, not just individually, but collectively, across very large distances, they noticed something that didn't quite fit this calm picture. Something subtle but persistent. A hint that, on scales where we expected stillness, there might be movement. Not random movement, but coordinated movement. Now, we are not quite there yet. We're still standing at the edge of expectation, still holding on to the idea of balance, still grounded in what the universe should be doing. And that is important, because without that baseline, we would have no way to recognize when something unusual appears. So for now, we rest in this quiet understanding, a universe that on the larger scales should not drift in any particular direction, a cosmos where motion exists, but cancels itself out, a vast system in gentle equilibrium. And as we take one step further, we begin to look more closely at what has actually been observed. Because sometimes, when you expect stillness, the smallest movement becomes impossible to ignore. If you keep that image in mind, a leaf resting on what appears to be a calm, still lake, it becomes easier to notice when something begins to change. At first, the movement is almost invisible. The leaf shifts slightly, drifts a little farther than expected, not enough to draw attention, not enough to seem unusual, but if you watch carefully and for long enough, a pattern begins to emerge. The leaf is not just wandering, it is being carried, gently, consistently, in a particular direction, and that is very similar to what scientists began to notice when they studied the motion of galaxy clusters on the largest observable scales. Now, measuring the motion of something as distant and enormous as a galaxy cluster is not simple. We cannot watch it move directly, the way we might watch a car drive down a road. The distances are far too vast and the timescales far too long. Instead, scientists rely on indirect methods, subtle clues carried by light. One of these clues comes from the way light interacts with hot gas inside galaxy clusters. These clusters are filled with extremely energetic particles, and when the ancient background light, the faint glow from the early universe, passes through this hot gas, it can be slightly altered. Not in a dramatic way, just enough to reveal information about motion. You can imagine it like this. If you speak while standing still, your voice sounds one way. If you speak while moving towards someone, the sound shifts slightly. Not enough to notice casually, but measurable with the right tools. In the same way, the background light passing through a moving cluster carries a faint signature of that motion. And by studying many clusters, hundreds, even thousands, scientists can begin to piece together how these vast structures are moving relative to the background of the universe. Now, based on our earlier expectations, we would anticipate that these motions would be scattered, some clusters drifting one way, others another. No strong pattern, no large-scale direction. But what the data began to suggest was something different. Instead of random motion, there appeared to be a subtle coherence, a shared direction. A large number of galaxy clusters seemed to be drifting together toward the same region of the sky, not rapidly, not dramatically, but consistently, like leaves carried along by a slow, invisible current. This phenomenon has been described, in more technical terms, as a kind of large-scale flow. but you can think of it more simply as this: a gentle, coordinated movement of matter across enormous distances. And what makes this observation so intriguing is not just the movement itself, but its scale. This is not a local effect. It is not limited to a single cluster or even a small group of clusters. It appears across vast regions of space, spanning distances so large that, according to our expectations, the motion should have averaged out. And yet, it does not. Instead, it persists. Now, as always, science approaches this with caution. The measurements are subtle, the signals are faint. Different studies have produced different results, and not all observations agree perfectly. Some analyses support the presence of this large-scale flow, while others suggest that the effect may be weaker or even absent. So we do not treat this as a confirmed fact, but rather as a possibility, a signal that is still being examined, still being tested, still being debated. And yet, even as a possibility, it carries an important implication, because if such a coordinated motion exists, then something must be causing it. Motion, especially on this scale, does not happen without reason. There must be a force, a pull, a gravitational influence guiding these clusters in a shared direction. And this brings us back to something we touched on earlier: gravity, the quiet force that shapes the universe. It pulls matter together. It forms galaxies and clusters. It influences motion across vast distances. But gravity, as we understand it, depends on mass. Something must be there to pull, a region of higher density, a concentration of matter, a kind of cosmic anchor. So naturally, scientists began to ask, what is in that direction? What is pulling these clusters? And in some cases, there are known structures, massive concentrations of galaxies that could contribute to this motion. But when researchers look more closely, something doesn't quite fit. The motion appears to extend beyond what these known structures can explain. It continues, even when it should begin to fade, and that is where the idea becomes quietly unsettling. Because if the motion does not diminish with distance, if it continues across scales where local influences should no longer dominate, then it raises a deeper question. What if the source of this motion lies beyond what we can see? Not hidden within the universe, but beyond the limits of our observation. Now, we are not making a claim. We are simply following the thread. Because this is how science works at the edge of understanding. One observation leads to a question. That question leads to a possibility. And that possibility opens the door to a new way of thinking. In this case, the idea is simple but profound. If there is a large-scale flow that cannot be fully explained by structures within our observable universe, then perhaps something outside that observable region is influencing it, not directly visible, not detectable through light, but still capable of exerting a gentle pull, like a current beneath the surface of a lake, invisible to the eye but unmistakable in its effect. And if that is even partially true, then the universe may not be as isolated as we once believed, because something beyond the horizon may be quietly shaping the motion within it. If you stay with that image for a moment, the quiet drift of galaxy clusters moving together as if carried by a slow, invisible current, there is a natural question that begins to rise. What could possibly move something so vast, across such immense distances? Because when we speak of galaxy clusters, we're not talking about small objects. Each cluster contains hundreds, sometimes thousands of galaxies. Each galaxy holds billions of stars. And all of that matter is bound together by gravity, forming structures so massive that they shape the fabric of space itself. To set something like that in motion, especially in a shared direction, requires a significant influence, not something small, not something local, but something extended, something that reaches across vast regions of space. And in our current understanding of the universe, there is only one force that operates effectively on those scales: gravity. Gravity does not push. It pulls, gently but persistently. It draws matter toward regions of greater density, areas where mass is concentrated. So if galaxy clusters are drifting together in a particular direction, the simplest explanation is that something is pulling them. Something massive, something distant, something we may or may not be able to see. Now, in many cases, we can identify these sources. There are enormous structures in the universe, regions where galaxies are densely packed, forming what are sometimes called superclusters. These structures exert gravitational influence over their surroundings, drawing nearby matter toward them. You can imagine them like valleys in a landscape. If you place a ball on a slope, it will naturally roll downward, pulled by gravity into the lowest point. In the same way, matter in the universe tends to flow toward regions of higher density. But here is where things become quietly intriguing. When scientists map the motion of galaxy clusters and compare it to the known distribution of matter, they find that the motion does not always align perfectly with what we can account for. In some cases, the direction of the flow seems to point toward regions that do not contain enough visible matter to explain the observed movement. And more importantly, the motion appears to continue, even across distances where the influence of known structures should begin to weaken. This is a key point, because gravity, while long-reaching, still follows a kind of gradual decline with distance. The farther you are from a mass, the weaker its pull becomes. You can think of it like standing near a large object. When you're close, its presence is strong and clear. As you move farther away, their influence fades, slowly, steadily. So if a particular structure is responsible for pulling galaxy clusters, we would expect its influence to diminish with distance. Clusters closer to it should move more strongly. Clusters farther away should feel less of its pull. But what some observations suggest is that the motion does not fade in the expected way. Instead, it appears to remain consistent across very large scales, as if the source of the pull is not confined to a specific region within the observable universe, but extends beyond it. Now, this is where we arrive at a concept that is both simple and deeply limiting. The observable universe. This is the region of space from which light has had enough time to reach us since the beginning of the universe. Because light travels at a finite speed, about 300,000 kilometers each second, there is a limit to how far we can see. Even if the universe extends much farther, we can only observe the part from which light has had time to arrive. You can imagine it like standing in a vast landscape on a foggy night. No matter how far the land stretches beyond you, your view is limited by how far the light can travel through the fog. There may be mountains, valleys, entire regions beyond your sight, but you cannot see them. The observable universe is like that. A horizon defined not by physical boundaries, but by the limits of light and time. And here is the important part. Just because we cannot see beyond that horizon does not mean nothing exists there. It simply means we have no direct information about it. But gravity is different from light. Light carries images. It tells us what something looks like. Gravity, on the other hand, shapes motion. It influences how matter moves, even across great distances, and in principle, its effects can extend beyond what we can directly observe. So this leads to a quiet but profound possibility. What if the motion we are seeing, the slow, coordinated drift of galaxy clusters, is being influenced by something beyond our observable horizon? Not something within our visible map of the universe, but something outside it, something we cannot see, but whose presence is felt through its gravitational pull. Now it is important to remain grounded. This idea is not confirmed, The data is complex. The interpretations are debated. Some scientists argue that the observed motion can still be explained by known structures or by statistical effects in the data. Others suggest that the signal is not as strong or as consistent as it first appeared, so we do not treat this as evidence. We treat it as a question, a possibility, one that invites further exploration. But even as a possibility, it carries a certain weight, because it challenges a quiet assumption we often make, that everything influencing our universe must lie within it, within the part we can observe. And yet, here we are, considering the idea that something beyond that visible boundary may be gently shaping the motion within it. Not dramatically, not in a way that disrupts everything, but subtly, like a breeze you cannot see, but can feel as it moves across your skin. And if that is true, even in part, then the universe may not be a closed system. It may be open, not wide open, not easily accessible, but just enough for influence to pass through, just enough for motion to carry the signature of something beyond. And as we continue, we will begin to explore that boundary itself, not as a solid wall, but as a limit of what we can know, a horizon that separates the visible from the unseen, while still allowing a faint connection between the two. If you stay for a moment with that quiet possibility, that something beyond what we can see might be gently influencing the motion within our universe, it becomes natural to ask a deeper question, not about what is out there, but about what we are able to see at all. Because before we can understand whether something lies beyond our view, we first need to understand the limits of that view. And those limits are not arbitrary. They are written into the structure of the universe itself. To explore this, it helps to imagine something simple. Picture yourself standing in a vast open landscape just before dawn. There is a light mist in the air, not thick enough to obscure everything, but dense enough that distant objects begin to fade. Nearby, you can see clearly. A few steps farther, the details soften, and beyond a certain distance, everything disappears into the fog. Now, the important thing to notice is this. The fog does not mark the end of the landscape. It only marks the end of what you can see. The land continues. The world extends far beyond your visibility, but your knowledge of it becomes uncertain. The universe is very much like that. There is a kind of horizon that surrounds us, not a physical wall, not a boundary we could touch, but a limit, defined by how far light has been able to travel. Light moves incredibly fast, about 300,000 kilometers every second. Even at that speed, it takes time to cross the vast distances of space, and the universe itself has a finite age. It has been expanding and evolving for about 13.8 billion years. That means that light from the most distant regions has only had a limited amount of time to reach us. If something is too far away, its light simply hasn't arrived yet. And so, no matter how powerful our telescopes become, there will always be a boundary, a distance beyond which we cannot see. This boundary is often described as the observable universe. It is the region of space from which light has had enough time to reach us since the beginning, and it is enormous. If we could measure its size, it would span tens of billions of light years in every direction. To say it softly, it stretches for about 46 billion light years from us in each direction, forming a vast sphere of visibility. But even that immense sphere is not the whole universe. It is just the part we can observe. Like the misty horizon in the landscape, it defines the limits of our sight, not the limits of reality. And that distinction is important, because it reminds us that there may be far more beyond what we can see, regions of space that exist, that evolve, that follow the same physical laws, or perhaps slightly different ones, but remain hidden from us simply because their light has not yet arrived. Now, there is something else to consider. This horizon is not static. As time passes, light from more distant regions continues to travel toward us. The observable universe slowly expands. We see a little farther, a little deeper. But even as it grows, there will always remain regions beyond reach, always something just outside our view, and that creates a kind of gentle separation, not between real and unreal, but between the known and the unknown, between what we can observe directly and what we can only infer. Now, when we think about the motion we discussed earlier, the coordinated drift of galaxy clusters, it becomes clear why this horizon matters. Because if something lies beyond that boundary, we cannot see it, we cannot map it, we cannot directly measure its properties using light, and yet it may still exist, and if it exists, it may still have influence. This is where the analogy of the fog becomes especially helpful. Imagine again that you are standing in that misty landscape. You cannot see beyond a certain distance, but suppose you notice something curious. The grass around you is gently bending in one direction. Leaves are drifting across the ground. There is a movement, a subtle, consistent motion. You cannot see the source, but you can feel its effect. A breeze. The breeze itself is invisible, but its presence is undeniable. And even though you cannot see where it begins, you can infer that it must come from somewhere beyond your immediate view. In the same way, if we observe motion in the universe that cannot be fully explained by what we see within our observable region, it becomes reasonable to consider that its source may lie beyond that horizon, not visible, but present, not directly measurable, but influential. Now, it is important to remain careful. This does not mean that everything unexplained must come from beyond the observable universe. There are many complex processes within our universe that we are still learning to understand, and it is entirely possible that what we see can still be explained by structures or effects that are simply difficult to detect. But the concept of the horizon introduces a powerful idea. It reminds us that our observations are inherently limited, that what we see is only a portion of what exists, and that occasionally the influence of the unseen may appear within the visible, not as clear images, but as subtle effects, as patterns, as motion, as quiet hints that something lies just beyond. And as we move forward, this idea begins to open a door. Because once we accept that there may be more beyond what we can observe, we can begin to ask a deeper question. If there is something beyond our horizon, how might it connect to us? Not through light, but perhaps through something more fundamental, something that does not depend on visibility, something that reaches across boundaries and gently shapes the structure of the universe itself. As you rest with that image of a horizon, soft, distant, and quietly limiting what we can see, it becomes natural to wonder about something deeper. If light cannot cross that boundary in time for us to observe it, is everything beyond it completely disconnected from us? Or is there something more subtle at work? Because while light defines what we can see, it does not necessarily define what can influence us. And this is where gravity enters the picture. Gravity is a familiar idea, but also a quietly mysterious one. It is the force that keeps your feet on the ground, that holds the moon in orbit around the Earth, that binds stars together into galaxies and galaxies into clusters. But on a deeper level, gravity is not just a force pulling objects together. It is a shaping of space itself. You can imagine space not as something empty, but as something flexible, something that can bend and curve. When mass is present, it changes the shape of this space, and other objects, moving through that curved space, follow paths that appear as if they're being pulled. A helpful way to picture this is to imagine a stretched fabric. If you place a heavy object on the fabric, it creates a dip. Now, if you roll a smaller object nearby, it will naturally move toward that dip, not because it is being pulled directly, but because the surface it moves on is no longer flat. This is a gentle way to think about gravity, not as an invisible string pulling things together, but as a change in the landscape through which everything moves. Now here is where things become especially interesting. Unlike light, which travels at a fixed speed and defines what we can see, the influence of gravity is tied to the structure of space itself. And because space extends beyond what we can observe, the effects of gravity may also extend beyond that visible horizon. To say this softly, gravity does not stop at the edge of what we can see. It is not confined to the observable universe in the same way that light is. If there is mass beyond our horizon, regions of space we cannot observe, those regions still contribute to the overall structure of space. They still shape it. They still influence how matter moves within it, even if we cannot directly detect them with light. You can return for a moment to the image of standing in the fog. You cannot see beyond a certain distance, but imagine that far beyond that fog there is a large hill. Even though you cannot see it, the slope beneath your feet may still be gently tilted because of it. You might not notice the hill directly, but you would feel its effect, a slight incline, a subtle pull. In the same way, if there are large structures beyond our observable horizon, their gravitational influence could, in principle, affect the motion of matter within our visible universe, not strongly, not in a way that dominates everything, but gently, subtly, enough to leave a trace. And this idea connects naturally with what we discussed earlier, the unexpected motion of galaxy clusters, the possibility that they are drifting in a shared direction. If such motion cannot be fully explained by the distribution of matter we can see, then it becomes reasonable to consider that unseen mass beyond our horizon may be contributing. Now, it is important to be precise in a gentle way. This does not mean that gravity acts instantaneously across infinite distances. Changes in gravitational influence still propagate through space over time. But the key idea here is that gravity is not limited by visibility. It does not require light to carry information to us. It is embedded in the geometry of space itself, and because of that, it opens a quiet possibility that we may feel the influence of regions we cannot directly observe, not through images, but through motion, through patterns, through the subtle shaping of space. And this brings us to a deeper reflection. Our understanding of the universe is built on what we can observe, but observation is not the same as existence. There may be layers of reality, regions of space, structures, even entire domains that lie beyond our observational reach, and yet they may still be connected to us through the underlying fabric of the universe, through gravity, through the shape of space, through influences that do not require direct visibility. Now, once again, we remain cautious. This is not confirmation, it is a possibility, one that emerges naturally when we consider both the limits of observation and the nature of gravity. There are still many alternative explanations for the observations we've discussed. The motion of galaxy clusters may still be explained by structures within the observable universe. The anomalies may still be statistical or due to processes we do not yet fully understand, but the idea that gravity can carry influence beyond what we can see opens a door, a quiet door, one that leads us to consider that the universe may be more connected than it appears, not just internally, but externally, connected perhaps to regions beyond our horizon, or even to structures that exist in ways we're only beginning to imagine. And as we take one step further, that door opens into a new kind of question. If influences can cross boundaries, if gravity can reach beyond what we can see, then perhaps the universe is not just surrounded by more space, but embedded within a larger structure, a structure with layers, with depth, with dimensions that extend beyond our everyday experience, and that is where our journey gently continues. From the edge of what we can know, to the possibility that reality itself may have more layers than we once believed. If you allow your thoughts to rest gently at that boundary, the place where visibility fades, but influence may still remain, something new begins to take shape. Up to now, we have been thinking about the universe as a vast expanse of space, endless in all directions, filled with galaxies, clusters, and the quiet glow of ancient light. And when we speak of beyond, we often imagine simply more of the same, stretching farther and farther outward. But there is another way to imagine it, not as something that extends endlessly in distance, but as something that has depth, not just outward, but layered. To explore this idea, it helps to step away from space for a moment and think about something more familiar. Imagine holding a book in your hands. Each page in the book is thin, flat, and self-contained. If you were a tiny creature living on one page, your entire world would exist within that surface. You could move left or right, forward or backward, but you would have no direct awareness of the pages above or below you. They would be close, extremely close, in fact, but completely hidden from your experience. Now imagine that each page represents a kind of world, separate, parallel, existing side by side but not directly interacting in obvious ways. From within one page, the others are invisible, not because they are far away, but because they exist in a direction you cannot access. This is a gentle way to approach an idea that some physicists have explored, the possibility that our universe might be like one of those pages, a thin layer of reality, floating or embedded within a larger structure. Sometimes this is described using more technical language, but we can keep it simple. Think of our universe as a kind of surface, and beyond that surface there may be additional dimensions, directions that are not part of our everyday experience, not directions like north or south, not like up or down, but something different, something that we do not directly perceive. In this picture, there could be other layers of reality, other surfaces, other universes, existing very close to ours, but separated in a way that makes them inaccessible, like pages in a book that never quite touch. Now, it is important to approach this idea gently. This is not something we have directly observed. It is a theoretical possibility, a way of extending our understanding of space and reality to explore questions that standard models do not fully answer. But even as a possibility, it offers something interesting, because it provides a framework, a way to imagine how different regions of reality might exist alongside one another without being immediately visible. And more importantly, it offers a way to think about interaction. Because if our universe is a layer, and if there are other layers nearby, then the question becomes, are they completely isolated? Or could there be subtle connections? Now, from within our page, most interactions would be confined to the surface itself. Light, matter, and the forces we experience would move within this layer. They would not easily cross into other layers, and that is why, if such layers exist, they would remain hidden. But there may be exceptions. There may be aspects of reality that are not entirely confined, aspects that can extend beyond a single layer. And this is where the idea begins to connect with everything we've explored so far. Because earlier, we considered the possibility that there might be influences beyond our observable horizon, forces that we cannot see directly, but whose effects we might feel. Now we are extending that idea slightly, not just beyond our horizon, but beyond our layer. beyond the surface of our own universe. And this changes the way we think about distance. Because if another layer exists, it might not be far away in the usual sense. It might be extremely close. Closer than any galaxy, closer than any star, and yet completely inaccessible, not separated by space as we understand it, but by a different kind of direction, one that we do not experience in our daily lives. You can return, again, to the image of the book. 2 pages can be pressed together, almost touching, and yet the worlds on those pages remain separate, unless something allows a connection between them. And that is the key idea. Not that multiple layers must exist, but that if they do, they provide a natural way to imagine how our universe might be part of something larger. Not isolated, but embedded, not alone, but one layer among many. Now, once again, we remain careful. This is not a claim, it is not a conclusion, it is a way of thinking, a framework that helps us explore possibilities suggested by the patterns and motions we've observed. And as we take one more step, the question becomes even more focused. If there are layers, if our universe is a kind of surface within a larger structure, then what, if anything, can move between them? What could carry influence from one layer to another? Not easily, not freely, but perhaps just enough to leave a trace. And that is where we turn next, to the one aspect of the universe that may not be entirely confined to a single layer, a quiet force that shapes everything, and may just possibly reach a little further than we once believed. If you rest for a moment with that image of layers, thin, quiet surfaces of reality, stacked close together like pages in a book, there is a natural question that begins to form. If these layers exist, are they completely separate? Or is there something that can pass between them? Because if there is even the faintest connection, if something can move or leak or reach from one layer into another, then the idea of an isolated universe begins to soften, not disappear, but become more open. And to explore that possibility, we return once again to something familiar: gravity. We've already seen how gravity shapes the motion of galaxies, how it influences the structure of space, how it may even carry information from beyond what we can see. But there is another quiet property of gravity that makes it different from the other forces we experience. It is unusually weak. Now, that might sound surprising. After all, gravity feels strong. It keeps planets in orbit, holds stars together, shapes entire galaxies. But if you compare it to other forces that act at very small scales, it is remarkably gentle. A small magnet can lift a paperclip against the pull of the entire Earth, which means that, in a certain sense, the electromagnetic force in that tiny magnet is stronger than the gravitational pull of an entire planet. This has puzzled scientists for a long time. Why is gravity so much weaker than the other forces? Why does it seem so diluted? One way to think about this, again, gently, as a possibility, is that gravity may not be confined in the same way as other forces. Imagine speaking in a quiet room. Your voice travels through the air, filling the space around you. Now imagine that the room is not perfectly sealed. There are thin walls, small gaps, perhaps even open spaces beyond. As you speak, some of the sound does not stay in the room. It leaks out. It spreads into the surrounding space. From inside the room, your voice sounds softer than it would if everything were perfectly contained. Not because you're speaking more quietly, but because part of your voice is going elsewhere. Now return to the idea of layers. If our universe is like one of those pages, one layer among many, it is possible that most forces are confined to that layer. They operate within it. They do not easily cross into others. But gravity may be different. It may not be fully contained. It may extend beyond our layer, spreading to the larger structure that surrounds it, and if that is the case, then from our perspective, gravity would appear weaker. Not because it is inherently small, but because it is shared, distributed across more than just our universe. Now, this idea is still speculative. It is one of several ways scientists have tried to understand the nature of gravity, but it has an interesting consequence. Because if gravity can extend beyond our layer, then it may also carry influence from beyond our layer, not in a direct or dramatic way, but subtly, quietly, just enough to leave an effect, just enough to shape motion, to create patterns, to gently nudge the structure of the universe. You can return again to the analogy of sound. Imagine two rooms separated by a thin wall. In one room, someone is speaking softly. In the other room, you cannot see them. You cannot hear every word clearly. But you can detect something, a faint murmur, a vibration, a sense that there is activity on the other side. You do not have full access to that other space, but you're not completely isolated from it either. And this is the kind of connection we're considering here. Not a doorway, not a direct passage, but a subtle exchange, a leakage of influence, a quiet interaction across layers. Now, if something like this is possible, it offers a way to think about many of the features we've explored. The anomalies in the cosmic background, the patterns that seem slightly too structured, the motion of galaxy clusters that appears to have a shared direction. All of these could in principle be influenced by something beyond our immediate layer of reality. Not something visible, not something we can directly interact with, but something that leaves behind faint traces. And this idea does something important. It connects the abstract concept of other realities to something more physical, more grounded. Because instead of imagining completely separate universes with no interaction, we begin to imagine a system where interaction is possible, but limited, subtle, rare, difficult to detect. Now, as always, we remain careful. There's no direct evidence that gravity behaves this way. There are alternative explanations for its apparent weakness. There are many models, many interpretations, and no single answer has been confirmed. But the idea remains valuable, because it provides a bridge, a way to move from the observation of anomalies to the possibility of interaction, without requiring dramatic assumptions, without breaking the known laws of physics, just by gently extending them. And in doing so, it invites us to consider that the universe may not be sealed, not completely, that there may be a quiet exchange between what we can see and what lies just beyond, not loud, not obvious, but present, like a faint sound through a wall. And as we move forward, we will begin to gather together the final pieces of this story, because beyond patterns, beyond motion, beyond layers, there are still small signals, subtle hints in the background of our observations, quiet traces that may not prove anything, but suggest that something more may be there, something just beyond the edge of perception. As your thoughts settle into this quiet possibility, that our universe may not be entirely sealed, that there may be subtle connections beyond what we can directly observe, it becomes natural to ask one final kind of question. If such connections exist, would we see only large patterns and motion? Or might there also be smaller, quieter signals, hidden in the background? Because sometimes the most interesting clues are not the ones that stand out clearly. They are the ones that almost blend in, the ones that feel like noise, until you listen a little more, carefully. To explore this, imagine sitting in a quiet room late at night. Everything seems still, but if you pay close attention, you might begin to notice faint sounds, a distant hum, a soft vibration, perhaps the quiet echo of something happening just beyond your awareness. Individually, these sounds might not mean much. They could be explained in many ordinary ways, but occasionally something doesn't quite fit. A tone that is just a little too strong, a pattern that repeats more than expected, a signal that lingers when it should fade. And this is very similar to what scientists sometimes encounter when they study the universe at its most subtle levels. One example comes from the study of radio waves, the low-energy signals that fill space in addition to visible light. When researchers measure the background of these radio waves, they expect to find a certain level of intensity, a baseline, something that can be explained by known sources such as distant galaxies and other cosmic processes, but in some observations the background appears to be stronger than expected, not dramatically so, but noticeably, as if there is an extra layer of sound in the cosmic quiet. You can imagine it like tuning a radio. You expect a certain level of static, but instead the static is slightly louder than it should be, not enough to overwhelm everything, but enough to make you pause and wonder where it is coming from. Now, as always, there are many possible explanations. It could be that there are more distant sources than we currently account for, more galaxies, more faint emissions, more subtle processes contributing to the signal. Or it could be that our models of these sources need refinement, that we are underestimating how much background radiation they produce. These are all reasonable possibilities, and they are actively explored. But the fact remains that, at times, the background seems a little too full, a little too rich, and that opens the door, just slightly, to the idea that there may be contributions we do not yet fully understand. Now, there is another kind of subtle signal that has drawn attention, one that is even quieter, even more delicate. It comes from experiments designed to detect something we cannot see directly. Dark matter. Dark matter is thought to make up a large portion of the universe's mass, and yet it does not emit light. It does not reflect it. It does not interact with it in ways we can easily detect. We know it is there because of its gravitational effects, because of how it influences the motion of galaxies and clusters. But beyond that, it remains elusive. Now, some experiments have attempted to detect dark matter not by seeing it, but by observing how it might interact very weakly with ordinary matter. In certain cases, researchers have reported signals that appear to vary over time, a gentle, repeating pattern, a kind of seasonal rhythm. You can imagine it like a soft wind that changes direction slightly as the Earth moves through space. As our planet orbits the Sun, and as the Sun moves through the galaxy, we pass through different regions of space. If dark matter is present as a kind of background flow, then our motion through it might create a subtle variation in how often it interacts with detectors. Like walking through a light drizzle, sometimes you face into the rain, sometimes it comes from behind. The pattern shifts slightly with your motion. Now, these signals are extremely faint, and they're not universally accepted. Different experiments have produced different results. Some detect variations, others do not. So once again, we remain cautious. These are not confirmed discoveries. They are hints, possibilities, signals that sit just at the edge of detectability. But when we place them alongside everything else we've explored, the anomalies in the cosmic background, the large-scale motion of galaxy clusters, the limits of observation, the possibility of layered reality, they begin to feel like part of a larger picture. Not a clear picture, not one we can fully resolve, but a suggestion that the universe may be more complex than it appears, that there may be subtle influences, quiet interactions, faint signals that do not fit neatly into our current understanding, and that these signals, while small, may be pointing towards something deeper. Now, it is very important to hold on to a sense of balance here, because science does not build conclusions from hints alone. It requires consistency, reproducibility, clear evidence that can be tested and confirmed, and we are not there yet. Not with these signals. They remain uncertain, debated, open to interpretation, but they serve a purpose. They remind us that the universe is still full of questions, that even in the quiet background, the soft hum of cosmic radiation, the faint interactions of unseen matter, there may be clues waiting to be understood. And as we bring everything together, these subtle signs help guide us toward a final reflection, not about what we know with certainty, but about what we're beginning to suspect, that the universe we observe may not be the whole story. And so, as we gently gather all of these threads together, a quiet picture begins to form, not a sharp image, not a complete answer, but something softer, something that feels just slightly out of focus, yet meaningful all the same. We began with a comforting idea, a universe that is smooth, balanced, and the same in every direction, a cosmos that behaves predictably, where large-scale patterns average out and no single region stands apart. And for the most part, that picture still holds. The universe is remarkably uniform, elegant in its structure, consistent in its behaviour. But as we looked more closely, more carefully, more patiently, we began to notice small deviations, tiny irregularities, a slight imbalance across the sky, a region colder than expected, a vast stretch of space where matter seems to be missing, faint circular patterns that hint at echoes of something long past. None of these on their own demand a new explanation. Each one can be understood, at least partially, within the framework of what we already know, but together they begin to feel different. They begin to form a pattern, not a loud one, not a definitive one, but a quiet suggestion that the universe may not be perfectly uniform after all. And then, as we shifted our attention from structure to motion, another layer of the story emerged. Galaxy clusters, moving together, drifting in a shared direction, as if carried by a gentle current that spans distances far larger than we would expect. And once again, this motion does not clearly break our understanding, but it stretches it. It asks us to consider whether there may be influences we cannot fully account for, influences that extend beyond the visible distribution of matter, and that brings us to the edge of what we can know, the horizon, a boundary not of reality but of observation, a limit defined by the speed of light and the age of the universe. Beyond it, there may be more, much more, but we cannot see it directly. We can only infer its existence through indirect effects, through motion, through patterns, through the subtle shaping of space. And when we consider gravity, the quiet force that curves space and guides motion, we find that it does not respect the same limits as light. It does not depend on visibility. It is woven into the fabric of reality itself, and because of that, it offers a bridge, a way for influence to extend beyond what we can directly observe. From there, we took one more step. We allowed ourselves to imagine that the universe might not be a single, isolated expanse, but part of something larger, a structure with layers, with depth, with dimensions that lie beyond our everyday experience. Not as a dramatic claim, but as a possibility, a way to make sense of connections that might otherwise seem difficult to explain. And within that picture, we considered one final idea. That gravity, unlike other forces, might not be entirely confined, that it could extend beyond our layer of reality, that it might carry with it the faint influence of something beyond, not strongly, not clearly, but just enough to leave a trace. And finally, we turn to the quietest signals of all, the background, the faint excess of radio waves, the subtle variations in experiments searching for unseen matter, signals that do not confirm anything on their own, but gently suggest that there may be more happening than we currently understand. Now, it is important to pause here, to rest in the uncertainty, because nothing we have explored tonight provides definitive proof of another reality. There is no clear boundary we can point to, no direct observation that confirms the existence of other layers, other universes, or external influences. What we have are hints, patterns, tensions in the data, possibilities that arise when our models do not quite align with what we observe. And this is a familiar place in science, a place where curiosity lives, where questions are more important than answers, where the unknown is not something to be feared, but something to be explored, gently, over time. Because the history of science is filled with moments like this, moments when the data begins to whisper that something is incomplete, that our understanding, while powerful, is not yet finished, and often those whispers lead to deeper insights, new frameworks, new ways of seeing the universe. So what does it mean then to consider that our universe may not be alone? Perhaps it does not mean that there are other worlds just beyond our reach, waiting to be discovered in a dramatic way. Perhaps it means something quieter, that reality is layered, that what we see is only part of a larger structure, that the universe is not a closed system, but one that is gently connected to something beyond, not in a way that disrupts our daily lives, not in a way that changes the stars in the sky, but in a way that leaves subtle traces, small patterns, quiet motions, faint signals in the background. And there is something strangely comforting about that, because it suggests that the universe is not isolated, that it is part of something larger, something we're only beginning to sense. And as you let that thought settle, you might find that it does not demand a clear answer. It does not need to be resolved. It can simply exist, like a soft question in the back of your mind, a gentle curiosity, a quiet sense that there may be more, just beyond the edge of what we can see. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully wherever and whenever you may be.